Lesson 4.3 is an introduction to logarithms, and there is a relationship between a logarithm and an exponential expression. Now, I don't really like having to memorize this, so I'm going to teach it in a slightly different manner. All right, so let's just, on this side, I'm going to graph the exponential function a to the x, and on this side I'm going to graph the logarithmic equation log base a of x. So notice that they have the same base. A is the base of the exponential, and a is also the base of the logarithm. So over here, graphs of exponential functions, we just did those. Right, so let's assume a is greater than 1. Right, so this is going to be an exponential growth. And if I put 0 in for x, a to the 0 is 1. So this graph is going to go through 0, 1. And exponential functions grow exponentially to the right, and then they kind of decrease down to 0 on the left. And all exponential equations have a horizontal asymptote, and this one happens to be at y equals 0. So there's some things I know about this graph. First, it goes through the point 0, 1. Right? We know the domain is all real numbers, and we know that the range is only positive numbers. Right? So the relationship between exponential functions and logarithmic functions is that they're inverses of each other. So when we did inverses, that's when we drew the line y equals x on our graph, right? And then we reflected this graph over this diagonal line. And a couple things happened, right? The points switch. If 0, 1 is on a to the x, then 1, 0 is on the inverse. The domains and ranges are going to switch, right? The horizontal asymptote here, when we reflect it over this 45-degree angle, is going to become a vertical asymptote. So over here, I'm going to make all those changes. So I'm going to draw my axes here, okay, and that y equals x function, right? So log base a is the inverse of a to the x. So log base a is going to have the point 1, 0 on it. And if a to the x has a horizontal asymptote at 0, then log base a is going to have a vertical asymptote at 0. And then let me go ahead and fill out the domains and ranges, because the domains and ranges of inverse functions swap. So the domain of a to the x is going to be the range of log base a of x. And the range of a to the x is going to be the domain of log base a. And then if I reflect this over this line, okay, it's going to approach 0 as it goes to negative infinity, and then it's going to go and increase ever so slightly on the way out, right? So this is the graph of log base a, and the relationship is that they're inverses of each other. All those properties we learned about inverse functions apply here, right? So if we had 2 to the x, then the inverse of that would be log base 2 of x, right? And then we can do that for any positive number here, 3 to the x, 4 to the x, 5 to the x, okay? If their bases match, then they're inverses of each other. So first we're just going to kind of walk through the different logarithmic and exponential forms, right? So example 1 gives you both the logarithmic form and the exponential form. And they're just using this relationship here. But I would like to show you an easier way than memorizing that. All right, so let's start with the logarithm. The first one says we have log base 10 of 100,000 equals 5. All right, so they actually kind of solved the logarithm. So if you will, the argument of the logarithm is here, and the books are really bad about dropping those parentheses, but really there should be parentheses around this argument. All right, so if I wanted to change this logarithm to its exponential form, I want to cancel log base 10. And so because exponentials and logarithms are inverses, it's the exponential that's going to cancel this log base 10. So I'm going to raise both sides by 10 here. So this now reads 10 raised to the power of log base 10 of 100,000 equals 10 raised to the fifth. Right? So the exponential base and the logarithmic base, because they're inverses, they're just going to cancel out. And we get 100,000 equals 10 to the fifth. And this is true, all right? Because the easy way to evaluate 10 to a power is you count up how many zeros. 10 to the fifth power should have 5 zeros, right? So we have a logarithmic equation, and then we have the exponential equation. And we're just getting that by doing the inverse property there. So let me go ahead and do these other ones here. The next logarithm says log base 3 of 8 equals 3. Right? So it might, oops, it doesn't say log base 3, it says log base 2. Can't read it. All right, so it might be hard to think logarithmically, so we want to put this logarithm in its exponential form. So if I want to cancel log base 2, I'm going to raise both sides by 2. And the 2 raised to log base 2 is going to cancel. And all we're left with on the left-hand side here is 8. And then on the right we have 2 to the third power, right? Because when we raise both sides by 2, 2 is the base, and then the 3 is the power. So is 2 cubed 8? Absolutely. Okay. All right, so then let's go and do the next one. Log base 2 of 1/8 equals -3. Right? So if we were to put that in its log or in its exponential form, I would just want to cancel this log base 2. And so I'm going to raise both sides by 2. And 2 raised to log base 2 will cancel. And so we get 1/8 over here on the left. And on the right we get 2 to the -3rd power. Now is that true? Right? What do those negative powers do? Right? So 2 to the -3rd. If I wanted to evaluate this, I can't leave that exponent negative. I need to make it positive. And so we can make that exponent positive by putting it in the denominator. Right? So I'm just moving it. It's in the numerator right now, technically over 1. So if I move it to the denominator, then that's going to make this exponent positive. And 2 cubed is 8, and so I do indeed get 1/8. All right, so 2 to the -3rd power is 1/8. So we started off with the logarithmic form, and then we're using that to double check our exponential form. All right, one more. Letters are kind of hard to read. I think it says log base 5 of s equals r. Right? So this one we can't really evaluate. We can just write it in its exponential form. But the exponential form we can get by canceling the log. So this is log base 5. So if I want to cancel log base 5, I'm going to raise both sides by 5. And so the 5 raised to log base 5 cancels, and I get s equals 5 to the r power. Right? So instead of memorizing that relationship that's at the top of this page, just think about exponentials and logarithms being inverse functions, and they cancel each other out. All right, evaluating logarithms. Here, you know, if there was no equals here, what is log base 10 of 1,000? Let me show you how to do that. Okay, so this is how I would do that. If it just said, what's log base 10 of 1,000, right? And there was no 3 there. Okay, the answer is going to be 3, but let's put an x there, like we didn't know what that logarithm was. So I'm going to evaluate this and solve this for x by putting in its exponential form. So I want to cancel log base 10. So I'm going to raise both sides by 10. The 10 to the log base 10 cancels, and I get 1,000 equals 10 to what power? Okay, so what does the power of 10 need to be? Now, you can get your calculator out here and do 10 squared, 10 cubed, 10 to the 4th until you match, right? But 10 to a power just is a matter of counting the zeros. So 1,000 has 3 zeros, so I know that this needs to be the third power, okay? So x equals 3. 10 to the third is 1,000. Right, so I kind of call this, solving this part right here, is just using, I don't know, just using mathematical magic, okay? You just stare at it long enough until you see the answer, or you can just plug it into your calculator until you find the answer, all right? So again, let's pretend the 5 isn't here. If we had log base 2 of 32, and we needed to evaluate that, make an equation out of it, set it equal to x, okay, and then solve this equation for x, all right? It's already solved for x. But put this logarithm in its exponential form, right? So if I want to cancel log base 2, I'm going to raise both sides by 2. The 2 raised to log base 2 cancels, and I get 32 equals 2 to what power, right? So if you know your powers of 2, great. Okay, if you don't, you can just plug them into the calculator here. So 2 cubed is 8. And I'm looking for 32. 2 to the 4th is 16. 2 to the 5th is 32. All right, so since 2 to the 5th power is 32 here, then I know x has to equal 5. All right, let's do the next one. Log base 10 of 0.1. Log base 10 of 0.1. All right. If I needed to evaluate that without using the calculator, I'd make an equation out of it, right? And then we want to cancel the log base 10. So I'm going to raise both sides by 10 here. And I get 0.1 equals 10 to what power, right? Now, in order to solve this one, it's better to get it out of the decimal form. Right, so if I wanted to write 0.1 not as a decimal, maybe as a fraction, this is 1/10, right? So I have 1/10 equals 10 to the x power, right? So you use your powers again, right? Your mathematical powers, and what does the exponent need to be, right? Well, we can see that the 10 is moving to the denominator, and we'd already talked about that. What moves numbers to the denominator is a negative power, right? So if I wanted to move just a plain 10 down to the denominator, that means x needs to be -1, right? And then I have solved the equation. All right, one more. Log base 16 of 4 equals 1/2. All right, log base 16 of 4. All right, let's say we don't know it's a half. All right, let's set it equal to x and evaluate this. So first thing, get it out of the logarithmic form into the exponential form. So I'm going to raise both sides by 16. So 16 raised to log base 16 will cancel, and I get 4 equals 16 to the x power. Right? Now, how do you go from 16 to 4? Right? You can divide. All right? That's kind of where your brain goes, but powers don't divide. All right? So we know the answer is 1/2, but why is the answer 1/2? All right? So the way we can go from 16 to 4 is we can do the square root of 16 is 4. And if you remember, the square root is the same thing as the 1/2 power. All right? So we have this rule of exponents, a to the m over n. Right? The m is the power of a, and the n is the root of a. So I could write this nth root of a to the mth power. All right? So I always kind of say to myself, power over root, power over root. All right? The p comes before r, if you will. But the denominator is always the root. So if we had a cube root, we'd have a 1/3 power, a 5th root, a 1/5 power, right? And this one here, this 16, really has a power of 1. There is no power there. So it's understood to be 1, all right? So in this case, 16 is being raised to the 1 over 2 because the power of 16 is 1, and the square root means we have the second root, right? So 16 to the 1/2 is 4. That means this x needs to be equal to 1/2, right? Now we have some properties listed, some special properties of logarithms. It's not necessary to memorize these, right? But they are interesting. So let's do log base a of 1. Now they're using base a here because it doesn't matter what the base is, right? It could be base 2, base 5, base 10, right? If you want to take the logarithm of 1, you're always going to get 0. Well, why is that? Okay, it's easier to understand this if you put it in its exponential form. So if I want to cancel log base a, I'm going to raise both sides by a, right? And the a to the log base a cancels, and I get 1 equals a to the 0. Right? I didn't mean to leave it in parentheses. I should have dropped the parentheses. But a to the 0 equals 1, that makes sense, right? So the exponential form is going to make a lot more sense to you than the logarithmic form, and that's fine, right? If you can understand this, then you know what the log base a of 1 is, right? Now the next one, log base a of a equals 1. Right? We can work this two ways. I'll go ahead and work it the second way down below. Right? Let's go ahead and get this in its exponential form first. Right? So if I wanted log base a and I wanted to cancel it, I'm going to raise a on both sides. So a is going to cancel the log base a, and I get a equals a to the first power. Well, this is true because even though the first a doesn't have a power of 1, it's understood to be power of 1. Right? So that one should make sense. Okay. Log base a of a to the x equals x. Right? If I want to get this in its exponential form, I'm going to raise both sides by a. Right? A to the log base a cancels, and I get a to the x equals a to the x. Right? Obviously that's true. Okay, so no matter what the base is there, we're always going to get a to the x equals a to the x. Right? A raised to the log base a of x equals x. Right? Now this one started in its exponential form. Right? So I'm going to go ahead and let the a raised to the log base a cancel, because that's what we've been doing on all the other ones. So if a raised to the log base a cancels, we're just left with x equals x. Right? So at any point in time, if you have an exponential function and a logarithmic function, you can let them cancel. All right? So down below, what's log base 5 of 1? Okay? Again, let's say we needed to evaluate this. We didn't know, okay, we don't remember those properties. Set it equal to x, right? And solve it. So if I raise both sides by 5, the 5 raised to log base 5 cancels, and I get 1 equals 5 to the x. Right? Your powers of observation here. What does the exponent need to be here to make 5 to what power equals 1, right? So obviously that power needs to be 0, and so x equals 0, right? And the answer is 0, right? All right, next one, log base 5 of 5 to the 8th equals what? We're not sure, okay? I know the answer is 8 right there, but let's say it equals x. Make it into an equation where you don't have that answer. Now here I have a logarithm base 5, and I have an exponential base 5 in the argument. We can allow these to cancel, but just the second way of evaluating the one above, right? We don't have to change this to its exponential form if we don't want to. The faster way is to go ahead and let this logarithm cancel this exponential. So if I do that, I get 8 equals x. And so the answer should be 8. Right, what's log base 5 of 5? Log base 5 of 5, right? So let's say we didn't know the answer. We're going to make it into an equation here. Set it equal to x. Right, now log base 5, and then we have 5 to what power here? Okay, they didn't write a power, but it's understood to be a power of 1. So I have a logarithm and an exponential right next to each other. Right? The exponential is inside the argument of the logarithm. We can let these cancel. Now be careful, because when you let these cancel, you get the power, right? And so the power of 5 was 1. And so we get an answer of x equals 1, right? And then last but not least, 5 raised to the log base 5 of 12 is what? Right? Is what? We've been doing these over and over, okay? Exponential raised, a logarithm inside the exponential, we can let these cancel, and we're going to get the answer is 12, right? So just kind of focus on the exponential cancels the logarithm cancels the exponential, and I think evaluating these get a lot simpler, okay? No real memorizing, it's kind of intuitive what you need to be doing. All right, so now we're graphing logarithms. So they've kind of built a table of values here, but I really want you to focus on where is the x-intercept, where is the vertical asymptote? Okay, and then probably domain and range as well. All right. So if we wanted to graph log base 2 of x, right, there's no shifting here. On the other ones, we're going to start shifting these up, left, right. We're going to reflect them. Okay, so you kind of have to keep all this straight. But a normal logarithm will have a vertical asymptote at 0 every single time, right? So here on the vertical asymptote, I'm going to put x equals 0. A logarithm will always go through 1, 0. So the x-intercept is 1, 0. And this x-intercept should be 1 unit away from the asymptote. And then we're just going to draw our logarithmic shape through that point, right? So here, just let it grow slowly to the right, and then hit the asymptote and go down on the left, right? Now, what's the domain here? Okay, how far left, how far right will this graph go? Right? Well, this graph clearly goes off to infinity, okay? But this graph doesn't pass 0, right? It's going to hit this vertical asymptote and never touch it, right? So the domain is 0 to infinity, and the range is all real numbers, right? All the way down, all the way up. All right, so let's look at the next. Oh, let me talk about, well, what about log base 5? right? The higher the base, the faster it's going to grow. So log base 5 is just going to be a little bit taller, okay, and it's going to go to the asymptote a little bit faster. So there's not much change. It's still going to go through 1, 0. It still has the same asymptote. Still has the same domain and range even, right? It's just going to grow a little bit faster. Actually, oh my God, I was thinking of exponentials. This is not log base 5. All right, apologize there. Log base 5 should go through 5, 1. Eek. So it's going to grow faster this way, not taller here. It's going to go out faster this way. All right, and so then log base 8 would be here. Okay, it's going to go through 1, 8. But I really don't, I'm not going to make you graph these exactly. Okay, log base 8 of x. Now, how did I know log base 5 is going to go through 5, 1? Log base 5 of x, okay, equals the y. Well, if I wanted to know where the y value was 1, I could put 1 in here for the y. Log base 5 of x equals 1. And then I can solve this, right, by raising both sides by 5, and I get x equals 5 to the first power. So if the y is 1, the x needs to be 5. And so it's going through the point 5, 1, right? I knew that. I don't know why I let myself get so confused, but there it is, all right? So log base 8 of x is going to go through 8, 1 for the same reason. We could do the 8 here, set the y equal to 1, cancel it, and we're going to get 8 to the first power equals 1. Same thing's going to happen there. All right, but a logarithm, the x-intercept, the vertical asymptote, the domain, and the range is what's important here. All right, so here they want you to graph negative log base 2 of x. This negative sign is a reflection, and this negative sign is on the outside. So this is a vertical reflection. Right. So a normal log base 2 of x is this increasing function here. Okay, goes through 0, 1. So if I were to reflect this graph, let me go ahead and draw this here. Okay, this is our regular function. Now if I were to reflect it, let me reflect it with purple here. Then this part, vertical reflection, means over the x-axis. So the part below the x-axis is going to get reflected up, and the part above the x-axis is going to get reflected below. Right? So there we have negative log base 2 of x. Right? What's the x-intercept? Still 1, 0. Right? What's the vertical asymptote? Still at 0. Right? X equals 0. What's the domain? Still all positive numbers. Right? What's the range? Still negative infinity to infinity. Okay? All that information remains the same. Now on the next one, they put the negative sign in with the x, right? The first one, the negative, was multiplied on the outside. This negative is on the inside of the argument here. So this negative is a horizontal reflection. And so if you wanted to reflect a graph horizontally, that'd be over the y-axis. So the entire logarithm form, log base 2, is here. It goes through 1, 0, right? Here's your original. Now, if I were to reflect that horizontally. So what's on the right goes on the left, what's on the left goes on the right. We get this graph, right, the mirror image over here. Now this will change some things, right? What's the x-intercept now? If we reflect it horizontally, this is crossing the x-axis at -1, 0. What about the vertical asymptote? Okay, the vertical asymptote didn't move, right? It's still at x equals 0. Now the domain here changed as well, because this domain, it's going to -infinity, but it's going to go to 0 and not past 0, right? It's just going to get closer and closer to 0. So we have a domain of -infinity to 0. It swapped it, right? And the range, how far down, how far up? Goes all the way up, all the way down. This is still all real numbers, right? All right, so now we're going to look at a shift. Okay, so again, this is log base 5. Okay, so it's going to go through 1, 0. It's going to go through 5, 1. Here's our original. Right? So if I did 2 plus log base 5, this 2 is being added to the outside. So sometimes it's better to think of this as log base 5 plus 2, where the plus 2 is the last part of the function. So we're taking the function and adding 2 to it. So this is a shift up. Okay, and when we shift a graph up, this point that was at 1 is going to go up 2 units. And so now we have a point at 1, 2. Right? So I'm going to call it the x-intercept because that's where the point moves. Sometimes I just call it the generic point. Right? So where is the point? It started at 1, 0. It got shifted up 2, and so now it's at 1, 2. Right? What about the asymptote? It gets shifted up, but it doesn't really move, right? So we still have an asymptote at 0. Domain still doesn't get past 0. So we're going to do 0 to infinity, and then the range, -infinity to infinity. Right? This next one, log base 10 of x minus 3. Okay. Here's our normal log base 10 of x right here. And we're going to shift this. So this minus 3 is not on the outside of the function, but it's inside with the x. So this is going to shift the graph to the left or the right. And because this is minus, we're going to shift to the right. Now when we shift to the right, okay, the asymptote is going to move and this point is going to move. Let's move the point first, all right? So if the point started at 1, 0, and I shift it to the right 3 places, 1, 2, 3. Now the point, okay, now the x-intercept is at 4, 0. And then the original asymptote was at 0. And that will get shifted to the right also. So if I shift the asymptote that's at 0 to the right 3 places, that's going to make the asymptote land here at x equals 3. And then the general shape is going to remain the same. Everything is going to get shifted to the right 3 units. Right? So when you shift to the right, you have to shift the asymptote and the point. But notice this x-intercept is still 1 unit away from that vertical asymptote. So x-intercept, or the point, I'm going to write 4, 0. The vertical asymptote moved to 3, so the equation for that vertical line is x equals 3. The domain, right? How far left, how far right? The domain is still going to infinity, but the domain is not going to go past 3, right? It's going to hit 3 and kind of hit that invisible wall there. So we're going to start this domain at 3. and go to infinity, right? And then the range, how far down, how far up? Ever so slightly, it's going to go up forever, and then it's going to go down to negative infinity as well. Right? So we get negative infinity to infinity. All right, so we have what's called a common logarithm and a natural logarithm. All right, so when they write a plain log with no base, it's understood to be base 10. So everywhere in this handout, they kind of wrote log base 10. The textbook is not going to do that, right? If they say what's log of 100, right? It's understood to be base 10. So if we had an equation like this that we wanted to evaluate log of 100 and there is no base there, okay, it's understood to be base 10. So if I wanted to cancel this common log, I would raise both sides by 10, and I'd get 100 equals 10 to the x power. Well, what does the power need to be? Well, how many zeros does it have? 100 has 2 zeros, so the power needs to be 2. Right? Now, the common log is the button on your calculator. Right? So if you had a calculator out, the log button, when you press this log button, it's going to do log base 10. Right? So log, let me go ahead and do 100 here. All right, so it's got log 100 on the screen. So if I hit enter, it should give me 2, right? Because we just evaluated that. But the log is base 10, right? So you can't do other bases using this logarithm button, right? And I'm going to leave it there. So graphing a common log is the same as it was before. Okay, it's going to go through 0, 1. It's going to have a vertical asymptote at 0, and it's just going to have that logarithmic shape. Everything about it is the same. All right. Let's go ahead and look at number 8 here. Because this is going to have us solve an equation. Okay, an equation with only variables in it, if you will. So the perception of the loudness B in decibels. So B is a decibel of a sound with physical intensity I is given by this equation. Okay, B equals 10 times log of I over I sub 0. Now I sub 0 is the physical intensity of a barely audible sound. Right? So barely audible. And then find the decibel loudness of a sound whose physical intensity is 100 times that of I sub 0. All right, so if I put I needs to be 100 times I sub 0. So if I sub 0 was 1, then 100 times that would be 100, right? So I'm going to plug that in and calculate this decibel level, right? So B equals 10 times log of 100 over 1, right? It appears that we can just plug this into the calculator. All right, let's go ahead and do that. Let's do 10 times log of 100 divided by 1. All right. Now, log of 100 should be 2, and 2 times 10 is 20. I think this answer is going to be 20. Okay, and it is. All right. But since this was like all numbers here, we could just type it into the calculator. So B is 20. That means the decibel level is 20 decibels. All right, it wasn't as hard as I thought it was. I thought we were going to have to solve it, but we didn't. We just plug numbers in. All right, moving on. The other kind of logarithm we have is what's called a natural logarithm. Okay, and that natural logarithm is log base e. All right. Now you're never going to see it written out log base e. They're always going to use ln. So if we had what's ln of 5, okay, equals what? If I wanted to cancel ln, right, the base of ln is understood to be e, right? Just like the base of a log is understood to be base 10, ln is always base e. So if I wanted to cancel ln, I'm going to raise both sides by e, and I get 5 equals e to the x, right? So maybe this is a bad example because we're not really going to solve for x here. If I wanted to do ln of 5, I could just type that into the calculator, right? The ln button is right below log here, right? So that, just remember this is log base e. So if I hit ln of 5, I'll get 1.609, right? 1.609. Now what's interesting here about this answer 1.609 is that what x equals. So if I did e raised to the 1.609, I should get a number approximately equal to 5, right? So let's go ahead and do that. Let's do e raised to the 1.609, right? So if I hit enter, now I did round that number, right? But we got 4.997, which is really close to 5. So if I had to type that whole decimal in there, I would have got even closer to 5. But it is telling us what we need to raise e to in order to get 5, right? So evaluating natural logarithms, because they haven't really given it to you, the same rules apply, right? So I have ln of e to the 8th here. How do we evaluate that? Well, ln is base e, and the exponential is also base e, right? Because this is e to the 8th power. So I'm just going to let these cancel. ln and e cancel each other out, and we're going to get 8, right? What is ln of 1 over e squared? Now you have to be careful here, because you can't let ln cancel e in the denominator. It has to be in the numerator, right? So if I wanted to write 1 over e squared, I need to move the e squared from the denominator up to the numerator. And the negative power is what's going to do that. So I can rewrite 1 over e squared as e to the negative 2 power. Because if it's positive in the denominator, it's going to be negative in the numerator. All right, so now we can go ahead and let ln and e cancel and get an answer of negative 2, right? And then we did this one above, right? What's ln of 5? Type it into the calculator, 1.609, blah, blah, blah. But that means that e to the 1.609 is approximately 5, okay, by the same reasons above. All right, how would we find just a domain without a graph? All right, what I want you to know, okay, and you do need to remember this, there's another rule for domains, right? We have to, for a fraction, we can't let the denominator equal 0. For a square root, we can't let the radicand be negative, right? For an ln, the argument can't be 0 and it can't be negative, right? So you need to remember that. Argument can't be 0 and can't be negative. Right? And I can show you a little reason why in just a moment. All right? But if the argument can't be 0 and can't be negative, that means this argument has to be positive. All right? So that means the argument must be positive. Which means the argument, in order to solve this, needs to be set greater than 0. Not greater than or equal to, because it can't equal 0. Right? It has to be greater than 0. So if I wanted to find the domain of this function, I would take the argument and the argument only, okay, no ln's, just take the argument and set it greater than 0, right? And then solve this. And so I get 4 is greater than x squared, right? Now, if I switched this around, okay, and wrote the x squared first, I'd get x squared is less than or equal to 4, right? Where is that true? For what numbers squared are going to be less than 4, right? We can square 2, we could square 1, 0, -1, -2, right? It's all the numbers between -2 and 2 here. Now, how can we solve that? You don't want to just take the square root, right? You kind of need to do some other work here. So let me bring the 4 back over. I want to know where x squared minus 4 is less than 0, right? And so what if I were to graph this? Okay, this is the graph of x squared, and it's shifted down 4 units. So if I were to graph this and shift the vertex down 4 units, here's my x squared, right? Now where is x squared minus 4 going to equal 0? At -2 and at 2, right? Because 2 squared minus 4 is 0. -2 squared minus 4 is 0, right? So I know the x-intercepts pretty well. And where is this parabola less than 0? Well, it's less than 0 here in the middle part, right? And so I know my domain is -2 to 2 only, right? Because that's what keeps this positive, right? I can't put 3 in there, I can't put 4 in there. It has to be less than 2. But it also has to be greater than -2 because -3 would make that negative as well, right? All right, so the graph of this is kind of interesting. But I think we're going to, no, I'll go ahead and work it. Okay, I got 2.5 minutes. All right. So if we were to graph this on the calculator, this is what we would get. All right. So it says use it to find the asymptotes and local and maximum local min values. Well, it looks to me like the asymptotes are located here, and it has 2 asymptotes. And that's because it can't go past 2 or -2, all right? So we have vertical asymptotes at x equals -2 and x equals 2, right? It's really closely tied to the domain. Now, they also want to find local max and local min values. So we have a maximum here and a minimum here. And the only way to calculate those without using calculus is to use the calculator, right? So I'm going to plug this function in, x ln 4 minus x squared, right? And then I'm going to graph it. Now this graph doesn't kind of extend forever, it kind of stops, but that's just a pixelation problem, right? So let me go ahead and change the window like the window on the paper. And the window on the paper just stopped at -3 to 3, okay, both on the x's and the y's. So now let me graph it. Here we go. All right. So this looks like it goes on forever, but it was just a pixelation thing before. So where is this local max and where is the local min? So you find that under the calc button. So calculate maximum, and then you want to scroll your cursor. It says left bound, right? So somewhere on the left, close but not too close, right? Hit enter and it'll draw a vertical line. Now I'm going to scroll to be on the right hand side and set my right bound, right? So now I have 2 vertical lines on either side of that maximum. Now the calculator says guess. So you enter one more time, it'll take your cursor right to the exact maximum. So we have a local max is what? Remember what the max value is. It is the y value only. So local max is 1.13, right? If you wanted to put the x, that's just where it occurs, 1.149, okay, but it has a local maximum value of 1.13. So we're going to do that same process with the minimum. So calc minimum, I'm going to move my cursor on the left-hand side of that minimum. Enter. Move my cursor to the right-hand side of the minimum. Enter. And then guess. Yes, you're the calculator. So enter one more time, and it gets me a local min is negative 1.13 when x equals negative 1.149. So it looks like this graph is symmetrical here. Not all graphs will be, so be careful. All right, all right, guys, that completes section 4.3.